Okay, so today I want to talk about hierarchical models. Well, first of all, how's the homework going for you guys? It was intended to be rather straightforward. You know, you run the deciphering code, and then you do Metropolis Algorithm for a multivariate thing, and then you do a Gibbs Sampler for a multivariate thing. And I'm hoping it feels okay. Anybody having major issues with it? All right. Well, I'm assuming you guys all started, and some people are nodding their heads, so I'm assuming this is good. Okay, so today we'll talk about hierarchical. Hierarchical, is that H-I-E? H-I-E, hierarchical models. Okay, so if we recall the beta binomial, okay, so let's recall beta binomial model. Okay, so the way the beta binomial model works is that we say, we have some kind of dichotomous outcome, right? So, yes or no, and the probability of yes comes from the probability of yes, not the probability, each outcome. So if we say, let's say y sub I is going to come from a Bernoulli with parameter theta, okay? So that is the probability of a yes is equal to theta, right? We'll say yes is 1 and no is 0 or something like that. Okay? And then, and we placed a beta prior distribution on theta, okay? So we'll say, so each, and theta itself comes from a beta distributions with parameters alpha and beta, right? And so so the beta distribution varies from 0 to 1, and, maybe it looks like this, or whatever it might be. Okay, maybe it looks like that. Okay, so you got some kind of distribution on the beta, and then what we found was that the posterior. So let's say we observe data vector y equal to kind of, y0, y1, y1, y2, y3, up to yn. Okay, so we have n observations. And then we said the posterior distribution that is the probability of theta given our data y. This is going to be is going to be another beta distribution, and we have alpha plus, I don't know, let me just say the sum of the y sub i's is equal to k. So it would be alpha plus k, and then we have beta plus n minus k. Right? And I'm hoping this is familiar. All right, so this is all review. How do I type on this thing? What is this? Okay, stats. Look at this, 102. I can do that. And it's week 9, Monday. Okay. Oh, Wednesday. Oh my gosh. All right. I forgot. We had Monday off. That accelerates everything so much more. Okay. Well, thank you. It's Wednesday. Get your head back in the game. All right. Okay. Let's see. So, and I think in the homework we did this baseball thing, baseball beta binomial thing, and we said, I said something like use alpha equal to 81 and beta equal to 219 or some arbitrary numbers, right? So we had the kind of the baseball homework example, and we used a beta distribution with alpha equal to 81 and beta equal to 219 or something like that, right? And there were questions like, how do we get alpha equal to 81 and beta equal to 219? And that's a good question. And the answer was, we kind of just felt like it, right? We said, when we do this and we look at 0 to 1, this thing will put most of its mass, most of the mass, is between like 0.2 and 0.35 or something, okay? Which reflected our prior feelings about batting averages, okay? But perhaps we are uncomfortable picking alpha and beta in such an arbitrary way. Okay, and so what we can do is we can treat alpha and beta themselves as random variables. Okay, and we can say the value for alpha 81 and the value beta 219, these are not fixed in stone, but these are values drawn from another random distribution. So we say instead, we can say alpha and beta are both random variables. And they are drawn from a distribution. Okay. All right. So let me, I'm going to use this example. So this is fat textbook called Bayesian Data Analysis, and you don't have to buy it or anything like that. But there is a good example in there on hierarchical models, and it's on like rat tumors, okay? And I'll link to like some guy's blog posts so that you can read a little bit more, okay? Okay. So what we have is a bunch of people have done scientific experiments with rats, and they look at whether the rats develop tumors or not. And apparently this is like fairly common that rats develop tumors. Like if a human develops a tumor, it's like a serious medical issue and you go to the doctor and you probably seek treatment right away. But, well, I guess rats aren't. Like a fairly significant number of rats develop tumors, and you know, I guess we don't care enough about rats to worry too much. But the proportion, you know, how often a rat develops tumor, it could be of interest to us, okay? And so what we have is we've got a bunch of data from previous experiments. Okay, so we actually have something on the order of 70 experiments. And we have, you know, the data is something like 0 out of 20, so 0 rats developed tumors, and there were 20 rats in the experiment. Okay, so we have stuff like that. You know, other experiments we had maybe, you know, 1 out of 18, maybe 4 out of 20, et cetera, et cetera, et cetera, okay? 70 experiments total. And then we have a current experiment that has some other data, okay? And so, you know, our current experiment, the 71st experiment, we have 4 out of 14 rats develop tumors. Okay, and so our hierarchical model here is that there is some alpha and beta out there, okay? Alpha and beta, these are the values that determine the beta distribution, okay? And from the alpha and beta, okay, so these determine the beta distribution. We draw some value, theta 1, okay? And from theta 1, we generate the values for our first experiment, okay? So we get alpha and beta, and from alpha and beta we draw kind of our first proportion, and then we flip kind of the coins or whatever, and we get this, right? And then you can imagine from we can draw another value of theta from alpha and beta, And those thetas are responsible for generating the data we see in the second experiment, okay? And so on and so forth. Until we get to our 70th experiment, and finally our 71st experiment. Okay, so this is kind of a graphical representation. There's something called a plate representation, and we would do it like this. We would say alpha and beta, and this is the same idea here. Do I use here? Theta sub S. Y sub S. Okay, and then we would write. And in this corner we would write S is equal to 1 to n. Okay, so this plate representation is the same thing. Okay, so this is a and the idea here is we have some alpha and beta up at the top, and from each alpha we are drawing a different theta value, and from that theta value we generate whether the rat developed tumors or not. Okay, you could imagine this also for the baseball thing. There might be some alpha and beta for all of baseball. Each baseball player has their own personal batting average. Okay, I mean, I don't know if things in real life are truly IID Bernoulli trials, but we could say, you know, each baseball player has their own theta, and when they step up to the bat and whether they hit the ball or not, that is just a Bernoulli realization of each individual theta. Okay. So this is what we have so far, and now we want to include alpha and beta as part of the parameters that we want to estimate. Okay, so rather than just saying alpha and beta are fixed and we're going to just figure out theta from the y, now we're going to say alpha and beta are random variables, and we also want to figure out those things based on the y that we see. So we now want a distribution on theta, alpha, and beta based on the data that we see y. Okay, so we want to include alpha and beta in our inference model. Okay, so so let me kind of just write our model here. So our model so far is that yeah, theta comes from the beta, and okay. So we want well, our model so far, yeah. Okay, we got theta coming from the beta distribution with alpha and beta, and then y coming from Bernoulli theta. And so our total joint distribution of theta, alpha, and beta, given the data, will be the probability of theta, alpha, and beta given y. So this is kind of our, maybe I'll just write our posterior joint distribution of all the parameters that we're trying to estimate based on the data that we have, okay? And from Bayes' rule, we can say that this is going to be theta, alpha, beta, and y divided by probability of y, okay? And this itself can be probability of y given theta, alpha, beta times the probability of theta, alpha, beta divided by the probability of y. Okay, is that all right? Okay, and so I'm just going to kind of look only at the top here. So we've got probability of y given theta, alpha, and beta times the kind of theta, alpha, and beta, right? So I'm just taking the numerator. This, we're just going to say it's proportional to this. All right, let's think about what our y is, okay? Y depends only on the theta. Okay, so the values of y depend only on the theta, so this thing will just be the probability of y given theta, right? So the theta is determined by the alpha and the beta, but once that theta is drawn, y is influenced only by theta. It has no direct relationship to alpha and beta. So this is what we have here, okay? And then here, I'm going to factor this out, okay? So we've got, so keep in mind, probability of y given theta, this is just a Bernoulli. Okay, and so I've got probability of y given theta. This is just kind of a Bernoulli thing. And then if we think about the joint distribution of theta and alpha and beta, I could say this is going to be the probability of theta given alpha and beta, right, times the probability of alpha and beta. This, you know, when you have a joint distribution, you can factor it into a product of one thing and its in a conditional distribution, right? So this is just using conditional probabilities. Yeah. Okay. And what is the distribution of theta given alpha and beta? Well, that is the probability of theta given alpha and beta. This is a beta distribution. Okay, and so our total posterior distribution of everything, theta, alpha, and beta, given our data y, is going to be proportional to this. Okay. All right. Is what I've done so far okay? All right. And so now we have this thing, and we have probability of A and alpha and beta. And so we have what we call a hyperprior distribution, right? Because our data is y, and it's determined by theta. Theta itself has a prior distribution, the beta distribution. And then we're saying the alpha and the beta itself have some kind of prior distribution, which we call a hyperprior distribution. And does that thing have parameters? And if so, should those also have like additional hyperpriors? And you can keep making your model more and more complex by continually having I don't know, more and more hyperparameters, until to infinity. But we don't want to do that, okay? Let me just copy this part right here. Oh no, how do I copy without my keyboard? Okay, I don't know how to do copy and paste. Can I do Control C? Okay, maybe that worked. Okay, well, whatever. All right, so new sketch. Oh yeah, we'll save this. Oh yeah, look at that. So this is what we have, okay? All right, so then what do we do about alpha and beta? Okay. So, we could have another distribution with more parameters. Okay. And these would be called hyperprior parameters, okay? One, probably a more desirable alternative is to choose an uninformative hyperprior distribution, okay? So an uninformative hyperprior distribution would be something that's like flat for all possible values. Okay, and the problem with uninformative hyperprior things is that they're often unbounded. So in the case of alpha and beta, they just need to be positive. Okay, and so they're just unbounded. It's from 0 to infinity, and that could cause problems in the integrals and stuff. So that's something we have to watch out for. So maybe to select an uninformative prior distribution. So this would be kind of like a flat, uniform distribution on maybe 0 to infinity. it could cause problems with unboundedness, but but this is what we have. Okay. The nice thing is that here we have a series of conditional distributions. We've got y given theta, theta given alpha and beta, okay? And then we just have this thing alpha and beta, right? And so this actually sets us up quite nicely for a Gibbs sampling setup, okay? So Gibbs sampling requires that we figure out kind of the conditional distribution of each parameter given the other ones, right? The only problem is figuring out this last one. What is the conditional distribution of alpha and beta given everything else, right? So we would say, you know, what's y given theta, okay? Or what's y given everything else? And really, it reduces just down to y given theta, because that's the only thing that matters, okay? And then we can do, you know, what's theta given everything else? So that would be theta given alpha and beta and y, okay? And we know how that works out because, you know, we figured out for a kind of a beta distribution, we know that it's going to be alpha plus the sum of the y's and the beta plus the other things. So we figured that out. The last part, you know, what is the probability of alpha or beta, or maybe both of them? Maybe we'll try to draw them both at the same time, given the theta and the y. That's a little bit more complicated, and we might not be able to figure out the conditional distribution, okay? But because of the Bayesian approach, we can probably figure out what it should be proportional to. And if we can figure out what it's proportional to, then we don't actually have to use Gibbs sampling for that step. We can just use the Metropolis algorithm. So we can kind of have this hybrid sampler that uses Gibbs sampling for the steps that feel natural in terms of having conditional distribution. And then when we get stuck with having some kind of distribution that's complicated and we're not quite sure what the full conditional distribution is, we can take advantage of the Metropolis algorithm, which only requires that we figure out what it should be proportional to, and we can draw samples that way, okay? Does that, well, I'll write this out. Okay, so what do we do about this? We're going to use an uninformative prior, and so anyway, we'll just have something unbounded here, okay? So basically, it's just going to be a constant, okay? So the probability of alpha and beta will be basically proportional to a constant for all alpha greater than 0 and beta greater than 0. All right, so then we can talk about drawing, you know, a sample from the posterior distribution using a hybrid of Gibbs sampling and the Metropolis algorithm. Okay. So we've got the probability of theta, alpha, and beta given y is proportional to the probability of y given theta, probability of theta given alpha and beta, times the probability of alpha and beta. And this is what we'll do. We will we sample theta from the conditional distribution of theta given alpha, beta, and y, right? Which we know is equal to the beta distribution of alpha plus, we'll say let k equal the sum of the y's, and beta plus n minus k. So this would be a Gibbs step. Okay, and I'm sorry, I think I misspoke earlier. I said we would sample y from everything else. We don't sample the y. The y is our data. We're treating our data as fixed, so we don't do that. So we just sample theta from here. This would be kind of the full conditional using Gibbs. And then we would have to need to sample alpha and beta from alpha and beta given theta and y. Okay. And this part, we can say, well, this should be proportional to the probability of, what is it? Well, it's going to be the proportional to alpha, beta, theta, and y. So this will also be proportional to y given theta let me think. Sorry. Alpha, beta given theta, and y will be, so it's the joint of everything, right? Alpha, beta, theta, y divided by the probability of theta and y. And yeah, so anyway, so the numerator part is still just going to be the product of everything. Theta given alpha, beta times the probability of alpha and beta. Okay, and this part will just boil down to a constant, maybe, but anyway. And we can use Gibbs sampling, not Gibbs sampling, we can use the Metropolis algorithm for this, okay? So we only know that it is proportional to this. Okay. We don't know the full conditional distribution. So we would use Gibbs Metropolis algorithm. Okay. Okay, so we have this kind of hybrid approach where we're combining Gibbs sampling using a full conditional, because this will be normalized. This thing, if we look at only kind of the numerator part, this will not be normalized. This will not integrate to 1. But the beauty of the Metropolis algorithm or the Metropolis Hastings algorithm is that it doesn't matter, okay? Is that if you can find out what it's proportional to, that the proportionality normalizing constant that should be present in the denominator, this piece, this is unknown, but this will cancel out at the end of the day during our Metropolis steps, okay? And so from here, we can get theta, alpha, and beta, all right? So here it's a Metropolis algorithm of alpha and beta together, and so we would probably need to use some kind of multivariate Metropolis step there. Okay, is that all right? Okay, well, I guess we're out of time. We'll end here for now. We'll take a look at this a little bit more in depth on Friday, and we'll see you guys then. Okay.